Hey there, this is Nick, and this is a short video to talk about how to use GDB, the GNU debugger. This is going to be a very brief overview of the higher level commands and such that you might generally encounter trying to use GDB, particularly to debug a higher level program such as one written in C. So I've thrown together a simple test program. It's basically a main program with a few variables, including a string. I throw a character string into this variable, and then I just have a for loop that iterates 10 times and does some semi-random arithmetic and calls a subroutine. The subroutine is called square. It doesn't actually do a square. It takes an incoming argument, reduces it modulo 10, multiplies by the other argument, and returns that. It's a nonsense program. It's just a way to have some code to go after in the debugger. So if we compile this using the regular GCC command, and we try to run it, invoke it with a GDB test. Well, if we just run test, it just prints out a number. It's no big deal. If we want to debug it, we can do GDB space test, and that will bring in the executable image. And you notice we get an error here saying that there's no debugging symbols found. So if I try to look at my source code, so I can say start to just start the debugger. And if I try to list my source code, there's no information available. So I can say examine 20 instructions starting at the program counter, and I can see the assembly language code for this version, and it does tell me, you know, this is 4 bytes past the beginning of my main program. This is 11 bytes past. And you can do some level of debugging like this, and function names are still preserved. So here's a call to my function square. But this is not a really convenient way to debug a program that was written in C. You can do it, but that's a separate topic altogether. So the better way to do this is when you compile your program, use a -G switch. That means include symbolic debugging information. So gcc-g, and then output to test.c. And now I can invoke my debugger GDB test. But this time it's going to read my symbolic information from my debug file. And this will give me a bunch of information about variable names and original source code instructions, which makes debugging a lot easier. So always begin by just saying start, and that will basically begin the execution of your program, and it will hit what's called a breakpoint. So it will stop executing at the beginning of your program. There's basically 2 modes you operate in inside the debugger. One is where the program itself is just free running, and you have no control over it other than using Control-C to interrupt it or typing in inputs and so on. The other is when you're sitting at this debug prompt, GDB, and here the program is temporarily halted, and you have the ability to do things like examine variables, examine source code, and so on and so forth. So at this point, we're at the GDB prompt, we have the ability to interact with the debugger. So the easiest command to use is just list. Say list, there's your source code. And it's reading this from the debug information that we compiled. So list will list 10 instructions around the current program counter. Any command that I type, if I just hit enter, it will repeat the last command. So if I want to do another list, I can just hit enter, and that means list the next 10 instructions. If I hit enter again, that will list the next 10. That takes me up to the end of my program. So here's a copy of my source code, and I can come back to this anytime I want. And it's telling me that I'm sitting at line 4 of test.c, which is this initial curly bracket. So I'm basically at the beginning of my main program. All right, what you probably want to do is single step through your program. So there's 2 ways to do this mainly. You can say step, which means go ahead and execute one of my source code instructions. So I'm sitting at that first curly brace. If I say step, it will go down to my first executable instruction, which is this sum equals 0. So it's about to execute this instruction. And I can say print sum, and there's my current value of sum. If I say step one time, that should have executed this instruction, sum equals 0. And now if I say print sum, and if I spell it correctly, I'll see that my sum is equal to 0. So $1, $2, these are local values that the debugger sets up that I can use to go back and refer to previous commands. GDB has, you know, a gazillion different features and options and parameters to it. I'm touching on like maybe 5 of the gazillion things that you can do with GDB. So you can always go and read online documentation on it and find all these embellishments. But this is just a high level view. So what have we done so far? We've done step to go ahead and step to the next line of instruction code, and we've used print to print out the value of a variable. So if I try to print the value of I, it tells me I is equal to 0. If I try to print the value of big, well, there is no big in the current context. And remember, our main program, we have two variables, I and sum up here. We have a subroutine with arguments big and temp and a variable I. All right, so let's just step through this and see what happens. I'm just going to say step, and it's going into a for loop. I'm just going to hit enter to do another step. So now in my for loop, I add I to sum, and then I call this routine square. When I hit enter again, it tells me I'm in my routine square, and I call it with arguments big equals 1 and temp equals 1. I set I equal to big. If big is bigger than 10, do I equals I modulo 10, return I times temp. There's the end of our subroutine, and now we're back in our main program at line 11, and we do another iteration of the loop, and I can keep stepping like this. And at any point I could say, for example, print big, and in here I can see what the value of big is. You can use P as an abbreviation for print. Most commands can be abbreviated to whatever length makes it unambiguous. So if I just say P big, that'll show me the value of P, of big, which is 9. So I can step and come back through, and if I just kind of bang on the return key, eventually I'll loop through 10 times, and then I'll exit. And once I exit, I can't step anymore because I'm out of my program. So if I want to rerun that, I can say start, and I can start doing some steps. So that's step. The other way to step through your program that's really useful is next. So you notice when I say step, I go into my loop, I say sum equals sum plus I call my subroutine, and now I start executing the codes in my subroutine. Suppose I'm not interested in what happens in that subroutine, I'm only interested in what's happening in my main program. Instead of saying step, I can say next. And next will look like step, except that when I call a subroutine, like here, if I say next, it won't single step through the subroutine. It will go ahead, call the subroutine silently, and after it returns, it will step to the next instruction of my current, the current main program that I'm in. So this is like a step over as opposed to a step into, if you remember those from assembly language programming. Step over will not go ahead and step through the subroutine calls. It will continue stepping after you return from the subroutine. So that's a little quicker way to step through a program if you know a subroutine is working correctly. So let's restart that again. And so that's step and that's next. We know about printing the value of variables. So let's step through a little bit here. There's sum equals 0. Now I'm going to copy hello into string, and since I did not compile string copy myself, that's part of the runtime library that was linked in, step automatically skips over all that code and moves on to the next instruction in my C code. But here I should have copied a string into this string hello. So if I say print string, it shows me the contents of that string. Now string was set up to be 120 characters, and you can see the first 6 characters are HELLO exclamation mark. That's what I copied into it. And then there's a null put at the end because strings are always null terminated. And then all of this stuff, this is the gibberish that you can potentially find showing up when you overflow an array bounds, or you return address that's pointing to the wrong thing or stuff like that. This is just random stuff that is inside our character array but has not been explicitly initialized by us. So that can be useful. The other way to examine things in GDB is to use the X function. So X is a much lower level function. P understands what type of variable something is and will show you the contents of that variable in an appropriate way. X is a much lower level way to examine memory inside the debugger. So for example, if I say X space string, that shows me 6C, 6C, 654E. What does all that mean? Well, the 48 is an H, the 65 is an E, and the two 6Cs are L and L. This is showing me the actual raw bytes that are sitting at the location designated string. The address of string is this big long thing, so I'm on a 64-bit machine obviously, and at that address I find 48, 65, 6C, 6C, If I do another X, it will examine the next 4 locations. There's a 6F, which is my O. There's the 21 exclamation mark. There's the 0, which is a null. Another 0, which is a null. And if I examine one more, the next byte is a 9. That's my \T, my tab, my control I. So we're examining raw memory at this point. If I did an x/b string, that would examine a single byte at that address. And if I do another x, it will show me the next byte. So now we can see that these things are in fact stored in the correct order, HELLO, exclamation mark, and then a null. If I did an x/10b string, it will examine byte by byte, but it will show 10 bytes in succession. So HELLO, exclamation mark, null, null, character 9, and so on and so forth. So there are lots of ways you can examine things in memory. Similarly, I could print the value of I that's equal to 0. That's not terribly interesting. Let's step through a little bit. So here's the value of big. That's a 9. And I could say x big. Let's not do that, because big is so when I did x string, remember is the address of the array because it's set up as an array. But big is just a value, but I could say print address big, and there's the location in memory where big is stored. And now if I say examine a single byte at that address, there's a 9. If I examine the next 3 bytes, I see a 0009. That's the value of the variable big, which is 9. So you get the idea. Hopefully you're just examining memory locations by using the X command. And again, there's a zillion modifiers on that. You can examine in different formats, different word sizes, and so on. So let's keep stepping through. Let's come back here. We're in a for loop still. We've iterated 2 times, so now I is equal to 3. Another useful thing to do is to put a watch variable on. So for example, I might say, let's watch the value of I. And I've set up a hardware watch point for I. And now if I start stepping, anytime that I changes, it tells me what the old value was and what the new value was. So that will set a watch point. I can step through. Down here it said I equals big. That did not trigger a watch point. Why? Because I'm inside a subroutine. So this is a different value of I. I is local. And this gets into the notion of call frames. A call frame has to do with what context you're looking at in your program. So when I call a subroutine, I have a different set of variables, such as I in this case, and that's obviously different from the I in the main program. So I can keep stepping through this. I'll come back. I'll get to the top of my for loop again, and here again I gets increased from 4 to 5, and so on. Alright, so I can also do a watch on a read. If I want to know when the value of I is read, I can say rwatch I, and now I've got a read watch point set up for I, and if I keep stepping, I'll go into my subroutine, come out of my subroutine. Here's my for loop, so that generates a watch point because I changed from 5 to 6. But then down here, my next line of code will say sum equals I, and that will generate a read watch point for the value of I. So it read a value of 6, then it added that to sum, and so on. So you can set up watch points like this, and if I say continue, which says just keep running until you hit a breakpoint, this will run my program until I hit something that's being watched. So continue gives a read watch point on I because it's calling a subroutine. If I continue again, it will generate a break when I change the value of I, and then here again when I read the value of I so that I can add it to sum. So here I'm stepping through my program very quickly, and the only time that anything is stopping my program is when one of these watch points gets hit. So that will exit my program very quickly. And let's go ahead and start again. So when I say start, it clears out all my watch points and my breakpoints and so on. So here's a listing of my program. Suppose I want to stop whenever I come back from, whenever I'm about to call my subroutine here, I want to stop execution of my program. I can make a breakpoint at line 13. So if I say break 13, it sets up a hardware breakpoint. Now here's the program counter address where it's breaking, but here's the line in my source code, line 13. So now if I say continue, it breaks when it gets to that line, and each time that I say continue, it runs through my code until I get back to that breakpoint. So here I'm just stepping through very quickly, and at each point I could print the value of sum, I could say continue, print the value of sum, and so on. Alright, so we've got steps, we've got next, we've got a way to print values, we've got breakpoints, we've got watch points, and we've got read watch points. So I could say watch, let's go ahead and start this program. And let's go ahead and watch sum. Let's do a read watch on I, and let's do a break at line 12. So I've got some debug set in, I run my code, and as I'm running it, I'm checking why the variables are changing the way they are, and at some point I say, hey, well, here's a problem, I is equal to 2. Okay, so I debug my code, I find what the problem is, and now I'm done with my watch points. I can say info watch and see all the watch points that I've set up. I can say info break and see all the breakpoints I've set up, which includes the watch points, and I can delete those if I like. For example, if I say delete 12, that will get rid of this breakpoint that I had at test plus 12, and so on. So so you can create watch points, breakpoints, you can get rid of them, and so on. A couple of other things to look at. So let's step through my program, and here's my string copy, here's the beginning of my loop, and now I call my subroutine, and I'm using steps instead of next, so I'll actually go into my subroutine. And now I'm in my subroutine, I'm at line 22, I equals big, and I'm doing an if statement. If I say BT, which means backtrace, I can see what my call frames look like. So this is telling me that my first call frame was at line 13 of my main program test. At that point, it called the subroutine square. And right now I'm sitting at line 23 in test, which is inside that subroutine square. This is like a stack trace. It's showing me what is called what, and what is that called, and what was the original thing called by, and so on. And all of my variables right now are in frame 0. They're in my current frame. So if I say print the value of big, it shows me the value of big. That's a variable inside the subroutine square. If I say print the value of sum, it doesn't know what I'm talking about because sum is declared in my main program. Right? So sum's a variable inside my main program, and it does not exist inside square. So printing sum doesn't work. If I look at my backtrace though, I see that frame 1 was my main program's frame. So if I say frame 1, now I've switched to the context of my main program, and if I say print sum, it will show me the value of sum. If here I say print big, it doesn't know what I'm talking about because big was declared in the context of my subroutine, which is frame 0. So if I go back to frame 0, I can print big, and there's the value of big, and now the value of sum is outside of my current context. So I can keep stepping and continue, and here's my value of sum is 1, my value of I is 2, so if I do a single step, sum should be equal to sum plus I, sum is equal to 3, so it's executed this instruction. It always shows you the instruction that's about to be executed. Okay, it stops before this instruction is executed. So right now sum is equal to 3, and if I call square, I'll go into my subroutine, I'll pass it a value of 3 and a value of I, which is 2. Suppose I realize that sum should have been equal to, I don't know, 23. So I could change my code, but I want to see what happens if I set sum to be the correct value. So I can say set variable sum equals 23, and now sum is equal to 23. And if I step one time, I call my subroutine square, but I pass my first argument is sum, which my subroutine calls big. I pass that as 23, and I pass I as 2. And now I can continue executing with that as the new value of sum. So you can set the values of variables inside your program using this set variable command, and that can be useful for debugging. Alright, that's a boatload of information. That's probably enough for now, but basic commands, list, step, next, print, X for examine, watch, rwatch, break. info watch, delete, BT for backtrace, frame for choosing a frame, and I think that's enough to get you going. When you're done, just say quit. It'll ask you if you want to quit because you're still running. Just say yes, and you're back to normal. All right, hope that helps. Have fun. Bye.